All right, so get this. We're going to try to build a whole universe, but we only have 1 second.
Okay.
Seems impossible, right?
Yeah.
Well, that's what we're diving into today based on this really incredible YouTube video I found from History of the Universe.
Oh.
And they break down how our universe, with all of its galaxies and stars and planets, could have formed from processes that happened in just the first second after the Big Bang.
It's really mind-boggling to think about, isn't it?
Oh, yeah.
Just the sheer scale of the universe.
Right.
Compared to this tiny little sliver of time.
It's why we're talking about going from nothing to everything in the blink of an eye.
Yeah.
But even before we get to that first second, the video throws out this crazy timescale.
Oh, yeah.
Zeptoseconds. Are you familiar with those?
Oh, absolutely. Yeah. Zeptosecond is so unbelievably short.
It's nuts.
Yeah. 250 billionths of a trillionth of a second.
Okay, so what can even happen in that amount of time?
Well, you'd be surprised.
Well,
scientists have actually managed to measure events.
Oh, wow.
That happen on that time scale.
So we can actually measure things happening in a zeptosecond. It just seems insane.
It is pretty wild.
Yeah.
But, when you think about it, the universe itself is 436 quadrillion seconds old.
Oh, my gosh.
So compared to that, a zeptosecond is like...
nothing.
Yeah, practically nothing.
Yeah.
Yet so much happened in that first second.
Right.
And even in those tiny fractions of a second within it.
Wow.
It's all about perspective, I suppose.
Okay, so I'm starting to see how even those seemingly insignificant fractions of a second could be so critical to the formation of the universe.
Yeah.
But let's go back to the very, very beginning.
Okay.
The video mentions this thing called the Planck epoch.
Yes.
Which sounds...
a very strange time.
intense.
Yeah, the Planck epoch is like the ultimate origin story. Yeah. It's the period within that first second where the universe was just a Planck length long.
Oh.
Things smaller than an atom.
Really?
It's a realm where our current understanding of physics just starts to break down.
So what was it like? Can we even imagine what the universe was like at that point?
Well, the video describes it as this quantum foam, which...
Quantum foam? What does that even mean?
So imagine a bubbling, frothing sea of energy where tiny black holes and wormholes are constantly popping in and out of existence.
What?
It's a place where even gravity as we know it didn't exist yet.
Okay, I need to take a breath.
Yeah.
That's intense. It's like trying to imagine the entire universe squeezed into my coffee cup or something.
It definitely stretches the limits of our imagination.
Yeah.
But what's even more fascinating is that from this tiny chaotic state, the universe underwent a period of rapid expansion.
Oh, wow.
Called inflation.
Inflation.
So in a fraction of a second, it grew by a factor of 10 to the power of 78.
Okay, hold on. So we went from a universe smaller than an atom to the size of a grapefruit, a basketball.
Think bigger. It's like a grain of sand suddenly expanding to the size of the observable universe.
Oh, okay.
And what's really cool is that the random fluctuations during this inflationary period are actually what seeded the large-scale structure of the universe we see today.
Really?
Yeah.
So you're saying that everything we see when we look up at the night sky, all those swirling galaxies, those vast clusters of stars,
yep,
it all stems from tiny quantum fluctuations in the first fraction of a second.
Exactly. It's like a cosmic echo of those early moments.
Wow.
And as the universe continued to expand and cool after inflation, those ripples in energy density, they started to clump together under the influence of gravity, setting the stage for the formation of stars and galaxies.
So we've got this massive expansion, and we've got the seeds for galaxies forming.
Right.
But what about the stuff that makes up those galaxies, the matter itself?
Yeah.
Where did that come from?
That's where things get even more interesting.
Yeah.
So as the universe cooled after inflation, the forces that govern the universe, like the strong force, the weak force, the electromagnetic force, they began to separate from each other.
Right.
And as they did, the first fundamental particles started to emerge.
But wait, I thought at the beginning of the universe there was an equal amount of matter and antimatter.
Yes.
So wouldn't they have just annihilated each other, leaving nothing behind?
You're absolutely right.
Okay.
There was this epic cosmic dance of creation and annihilation happening. Particles and antiparticles constantly colliding, releasing bursts of energy and disappearing back into the void.
Right.
But here's the key.
Okay.
As the universe continued to cool,
yeah,
a slight imbalance emerged, leaving a tiny bit more matter than antimatter.
Huh.
And it's this tiny excess that ultimately formed everything we see around us today.
So our very existence hinges on this cosmic imbalance.
It does.
This tiny bit of leftover matter from the first moment of Earth.
It really puts things into perspective, doesn't it?
Yeah.
And by the end of that first second, the universe was this incredibly dense, scorching hot soup of fundamental particles, resembling the heart of a neutron star.
Now, neutron stars are something else.
They're crazy.
The video mentioned that a teaspoonful of neutron star material would weigh as much as 8,500 Great Pyramids of Giza.
Yeah, they're so dense. How is that even possible?
Neutron stars are mind-bogglingly dense.
Yeah.
They're formed when massive stars collapse at the end of their lives.
Right.
And the protons and electrons in their cores get squeezed together to form neutrons. These neutrons are packed incredibly tightly, leaving no empty space.
Wow.
It's like cramming the entire mass of a mountain into a space the size of a city.
So you're saying that's what the entire universe was like at the end of that first second. That's intense.
It was a wild time, that's for sure.
Yeah.
But it also marked a crucial turning point.
Okay.
From that point on, the universe began to cool and expand,
setting the stage for the formation of the first atom and the emergence of the structures we see today.
Okay, so we've gone from quantum foam to a super dense particle soup in just 1 second.
Yeah.
I'm definitely starting to see how much can happen in such a short amount of time.
It's pretty incredible, isn't it?
It really is.
Yeah.
Wow.
It's amazing.
Yeah.
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 It really is amazing to think about all that unfolding in just a second, setting a stage for everything that came out.
Yeah, we've gone from a universe smaller than an atom to this super dense particle soup all in the blink of an eye.
Right.
But the video also talked about this alphabetical article.
Yes.
Which apparently had some problems.
Yeah, the alphabetical article was an early attempt to explain how all the elements in the universe were created in those first few moments.
Okay.
It's a great example of how science works. You know, we come up with theories, we test them, and sometimes those theories turn out to be wrong.
So what was the problem with this theory?
Well, it ran into a roadblock called the missing steps problem. Essentially, elements with atomic mass 5 at 8 don't exist naturally. It's like trying to build a staircase where 2 steps are missing.
Yeah.
You can't get to the top without them.
Right. So without those elements, the theory just couldn't explain how we got from a universe of mostly hydrogen and helium to the heavier elements we see today.
Exactly. And this actually led to a deeper understanding of how elements are formed.
Okay.
The alphabetical article, while incorrect, paved the way for our modern understanding of stellar nucleosynthesis.
Stellar nucleosynthesis, that's the process where elements are forged in the hearts of stars, right?
Exactly.
And here's where it gets really cool. Those elements that were created in stars, they're the same ones that make up you and everything around you. We're literally made of stardust.
It's a truly poetic concept.
It is.
But to understand how those stars formed in the first place, we need to rewind back to that first second.
Okay.
And talk about a crucial event called the cosmic freeze-out.
Okay, cosmic freeze-out sounds intriguing. What exactly happened during this freeze-out?
This is where it gets really mind-blowing because it all comes down to a tiny, tiny difference in mass.
Okay.
Between protons and neutrons. You see, neutrons are just slightly heavier than protons.
Right.
And in the early universe, the weak force, one of the fundamental forces of nature, was constantly flipping protons into neutrons and vice versa.
So protons could become neutrons and neutrons could become protons. That sounds like a pretty chaotic dance.
It was. But as the universe cooled, and the weak force weakened this dance, slowed down, and eventually a freeze-out occurred. The ratio of protons to neutrons became fixed with protons outnumbering neutrons by about 6 to 1.
Hold on, are you saying that this tiny mass difference is the only reason we have stars and galaxies?
It played a crucial role, that's for sure, if protons were heavier than neutrons.
Yeah.
The freeze-out would have favored neutron, and we'd have a universe dominated by helium.
Helium, but isn't helium like totally inert? It doesn't really react with anything.
Exactly. A helium-dominated universe would be a cold, inert expanse.
Wow.
Incapable of forming stars, planets, or life as we know it.
So we owe our very existence to the fact that protons are just a tiny bit lighter than neutrons.
We do.
Without that tiny difference, we wouldn't hear having this conversation.
It really highlights the interconnectedness of everything in the cosmos.
It does.
And, speaking of helium, its abundance in the universe is directly linked to that cosmic freeze-out.
Okay, I'm all ears. How does helium fit into all of this?
Well, remember how neutrons are inherently unstable on their own?
Mm-hmm.
They have a tendency to decay into a proton and an electron after about 15 minutes. But when a neutron pairs up with a proton to form a deuterium nucleus, it becomes stable.
So the deuterium nucleus is like a safe haven for the neutron?
Precisely. And most of that deuterium then combined to form helium, which is why helium is the second most abundant element in the universe.
Okay.
It's like a cosmic fingerprint, preserving a record of that early ratio of protons to neutrons from the freeze-out.
It's amazing how these seemingly unrelated things are all connected, right?
Absolutely. And there's this fascinating story about the discovery of helium here on Earth.
Really?
It was actually first detected in the sun's atmosphere.
Wow. Tell me more about it.
Well, in 1868, a French astronomer named Pierre Janssen was observing a solar eclipse in India when he noticed a strange spectral line that didn't correspond to any known element.
You know, I've always wondered how astronomers can tell what stars and galaxies are made of from millions of light years away.
That's where spectral lines come in. Each element has a unique fingerprint when it comes to light.
Oh, wait.
It emits or absorbs light at specific wavelengths, creating a unique pattern of lines in a spectrum.
Gotcha.
Janssen observed a new pattern.
Yeah.
Indicating the presence of an unknown element, which turned out to be helium.
So we went from thinking helium was this exotic element found only in the sun,
Right,
to realizing it's actually the second most abundant element in the universe. It even exists here on Earth.
and its abundance both in the universe and here on Earth is directly tied to those events that transpired in the first second after the Big Bang.
That's incredible. But to bring it back to our deep dive, the video also talked about these pristine clouds of hydrogen and helium observed by the Keck telescope in Hawaii.
Yes.
They described them as time capsules from the early universe.
Those pristine clouds are incredibly important because they offer us a glimpse into the universe just a second after the Big Bang, before the first stars ignited and began forging heavier elements.
So they're like the universe's baby pictures showing us what it was like before it grew up and got all complex.
That's a great way to put it. Their composition, purely hydrogen and helium, is a direct confirmation of what the universe was like before stars formed.
Okay, so we've got the cosmic freeze-out, the formation of helium, and these pristine clouds all pointing back to the events of that first second. But what happened next? How did we go from this hot, dense soup of particles to the stars and galaxies we see today?
Well, that's where things start to settle down a bit. But the story is far from over. As the universe continued to expand and cool, those protons and neutrons began to come together to form the first atom.
So we're finally getting to the point where the universe starts to resemble something we might recognize. It's pretty amazing that we can look back billions of years and see these echoes of the universe's earliest moments.
It is. And as the universe continued to cool and expand, those particles started coming together.
Right.
To form the first atoms, mostly hydrogen and helium.
Okay.
It was still incredibly hot, like around 10,000 degrees Celsius.
Wow.
So these atoms were stripped of their electrons, creating a state of matter called plasma.
So the early universe was basically like a giant glowing plasma ball, kind of like those cool plasma globes you see at science museums.
That is a great analogy.
Yeah.
But even within this hot plasma, gravity was starting to exert its influence, pulling those hydrogen and helium atoms together into denser and denser clumps.
So this is where gravity takes center stage and starts shaping the large-scale structure of the universe.
Exactly. Those clumps grew larger and larger over millions of years.
Wow.
Eventually becoming so dense and hot that nuclear fusion ignited in their cores, and bam, the first stars were born.
Talk about a cosmic light show. So these first stars were basically just giant balls of hydrogen and helium fusing together,
right,
releasing enormous amounts of energy.
Precisely. And these first stars were absolute behemoths.
Really?
Much larger and hotter than our sun.
Wow.
They burned brightly, but lived relatively short lives, eventually exploding as supernovae.
Okay, so we've got these giant stars forming, living fast and dying young, exploding as supernovae. What happens next?
Those supernova explosions were critical.
Okay.
Because they seeded the universe with heavier elements.
Oh, wow.
The intense heat and pressure within those exploding stars forged elements like carbon, oxygen, and iron,
right,
scattering them throughout the cosmos.
And those are the same elements that eventually went on to form planets and ultimately life itself. It's incredible how everything is connected from those first moments after the Big Bang to the very atoms that make up our bodies.
It truly is a remarkable story. And as those heavier elements spread throughout the universe, they mixed with the primordial hydrogen and helium, enriching the clouds of gas that would eventually collapse to form new generations of stars and planets.
So each generation of stars builds upon the previous one, adding more and more heavy elements to the cosmic mix. It's like a giant cosmic recycling program.
I love that analogy. And remember those pristine hydrogen and helium clouds we talked about earlier? The ones observed by the Keck telescope?
Yes.
They're like time capsules, showing us what the universe was like before those heavier elements from supernovae became widespread.
Right. They're like a glimpse into the universe's baby book before it became all decked out with heavier elements. It's incredible to think that we can actually observe these remnants of the early universe billions of years later.
It speaks to the power of science and human ingenuity to piece together this grand cosmic puzzle. And speaking of pushing the boundaries of our understanding, the video touched on this idea of a multiverse.
Ah, yes, the multiverse, the idea that countless other universes might exist with different laws of physics and different initial conditions. Is there any evidence to support this idea?
While we don't have direct observational evidence for a multiverse, there are theoretical models that suggest it's a possibility.
Interesting.
For example, the theory of cosmic inflation, which explains the rapid expansion of the universe in the first fraction of a second, naturally leads to the idea of a multiverse. It proposes that our universe is just one bubble in a vast expanding sea of other universes.
So there could be universes out there where protons are heavier than neutrons and everything is just a cold, dark expanse of helium.
It's possible.
Or universes with totally different laws of physics leading to unimaginable forms of matter and energy.
It's certainly a mind-boggling concept to consider. But even if we never have definitive proof of a multiverse, the very act of asking these questions expands our understanding of the cosmos and our place within it.
That's a good point. It's a reminder that we're still just scratching the surface of the cosmic mysteries that surround us.
We are.
But even with what we've learned about our own universe's first second, it's incredible to think about how much happened in that fleet.
It is.
Setting the stage for everything we see today, from the tiniest atoms to the largest galaxies.
It really is a humbling and inspiring story, and as we continue to explore the universe with new telescopes and instruments, who knows what other secrets we'll uncover about those first fleeting moments and the intricate tapestry of cosmic events that led to our existence.
Well, after this deep dive, I'm definitely feeling a sense of awe and wonder.
Yeah.
It's mind-blowing to think about how our very existence is intertwined with this grand cosmic story, all stemming from that first pivotal second.
It makes you appreciate the delicate balance that allowed our universe to evolve the way it did. And who knows, maybe someday we'll even find evidence of those other universes, those alternate realities with their own unique stories to tell.
And on that note, we'll leave you with this thought. Imagine a universe where that tiny mass difference between protons and neutrons had gone the other way. What would that universe look like? Could it support any kind of life? It's a question worth pondering as we marvel at the delicate balance that made our own universe and our very possible. Thanks for joining us on this incredible journey through the first second of the universe. Until next time, keep looking up, Lauren.